How do we take the derivative of an inverse trig function, you ask? We draw a triangle. So this is going to be a lot like how we kind of undid certain expressions with logarithms and exponentials to get them in a form that we feel comfortable with. The same thing is going to be true here. So let's start with just this fact. Y equals arcsine of x. Arcsine being the same thing, of course, as sine inverse. So if I know that y is equal to sine inverse, that means that y is equal to an angle whose sine value is x technically over 1. So I'm going to draw a picture. Sine inverse needs to be in either the first or the fourth quadrant. I'm going to choose to assume positivity here. Here's my angle y, the angle. My sine value needs to be x over 1. So the opposite over the hypotenuse is 1. Cool. Ms. Schwartz, how does that help us take the derivative? That is a great question. Well, I don't like that this says arcsine. So just like I would maybe take a log of both sides or raise both sides using exponentials, I'm going to choose to take the sine of both sides. So I'm going to get the sine of y equals the sine of the arcsine of x. Well, sine and arcsine are inverses, so they cancel each other out. This now says the sine of y equals x. Okay, still lining up with my triangle, right? The sine of angle y is equal to x over 1. Cool. Let's do some calculus. Take the derivative with respect to x. Well, the derivative of sine is cosine, leave the inside alone, times the derivative of the inside, dy dx. The derivative of x with respect to x is just 1. Okay, well, dy dx is what I was supposed to solve for. That's going to be equal to 1 over cosine of y. And this is an okay answer, but let's make this a better answer. Cosine of y, why leave that as, why leave that as cosine of y when I can find the cosine of y? If this is my triangle, my cosine is going to be this adjacent side over 1. Well, that adjacent side from the Pythagorean theorem, I would say x squared plus my adjacent side squared is equal to 1 squared. So my adjacent side is equal to the square root of 1 minus x squared. And it's going to be positive because I'm in the positive direction. So instead of cosine of y, I don't like that. Let's actually write in the cosine of y. The cosine of y is that adjacent side, technically over 1, but I'm not going to write it because it would be the same. So our dy dx is equal to 1 over the square root of 1 minus x squared. Some of you might have said, wait a second, Ms. Schwartz, I saw you wrote 1 over cosine of y. Isn't that the same thing as secant? Totally true. Dy dx here is also just equal to secant, if you like that identity better. Well, what is the secant of y? The secant of y is the hypotenuse over the adjacent. Boom, hypotenuse over adjacent. Either one works. All right, example 2, the arc secant. Find dy dx. Well, the first thing I want to do is draw a triangle. I know that the secant, which behaves like cosine, okay, the arc secant is the arc secant is x, all right? So I'm going to draw a triangle in either the first or second, because secant goes with cosine. Draw a triangle where my hypotenuse over my adjacent is x, so x over 1, okay? Because again, if cosine is adjacent over hypotenuse, then secant is hypotenuse over adjacent. So x over 1. Cool. I don't like that this says arc. So how do I get rid of the arc secant? I take the secant of both sides. The secant of the arc secant cancels out, and I'm left with the secant of the secant of y is equal to x. Well, that checks out. Here's my angle y, and its secant, the hypotenuse over the adjacent, is x over 1. Now I'm ready for calculus. The derivative of secant of y is secant times tangent times the derivative of the inside. The derivative of x is just 1. So to isolate dy dx, I'm going to have 1 over the secant of y times the tangent of y. Now it's my job to fill in the rest of those blanks using my triangle. If I need to find the secant of y, well, that I already have. The secant is just x over 1. So I can replace that as x technically over 1, okay? I also then need to find the tangent of y. Well, the tangent of y is going to require this side over here. Pythagorean theorem, this side ends up being the square root of x squared minus 1. You can check me on that. 1 squared plus that opposite side squared equals x squared. So that opposite side is equal to the square root of x squared minus 1. Cool. My tangent then is opposite over adjacent. Opposite from y being the square root of x squared minus 1. And then the adjacent is just 1, so technically over 1, but again, over 1 is all the same. Okay, here's what's going to happen next. You are going to pause the video. We have 4 more that we would need to prove. We have cosine, inverse, tangent, inverse, cosecant inverse, and cotangent inverse. And I want you to pick one of those and try to prove it through for yourself. I don't care which one. Figure out which of those 4 is your favorite remaining trig function. And go ahead and try that. Pause your video. Try one on your own with drawing the triangle and repeating the process. Unpause once you're ready to check your answers. All right, if you picked cosine, here's your work. Something you might want to notice is that this looks just like the derivative of arc sine, except, oh, shocking, the co-version is negative. Antiderivative of tangent, here's your work. You can pause it if you need to. This one is important to note because there's no square root that ends up, and this is now a bottom-heavy function. So, bottom-heavy functions, we've seen a lot of those with integrals. That could be coming back soon. Notice then for arc cosecant, looks just like arc secant, except co is negative. And arc cotangent looks just like arc tangent, except, negative. And again, arc cotangent, bottom-heavy, no square roots involved. Might come back to, I wouldn't say haunt us, might come back to show up later in our AP Calculus lives. Okay, we've got 2 more with a little bit of a twist, because now instead of just finding x, right, we know our cosine of x, let's talk about what happens when we make that inside a function of x, right? So we always know a chain rule kind of comes into play, but let's see what that actually looks like in terms of drawing the triangle, because the triangle is still important in trigonometry. So in this case, I'm looking for where an angle whose cosine is 7x over 9, okay? That's my angle y, has a cosine value, adjacent over hypotenuse, of 7x over 9. Well, I'm going to get rid of that arc cosine by taking the cosine of both sides. So now when I take the derivative, I'm going to end up with negative sine of y dy dx equals 7x over 9 is really 7/9 x, so its derivative is just 7/9. That means that dy dx is equal to 7/9 times 1 over negative sine of y. Okay, well, to find the sine of y, I need this missing side over here. This is going to be the square root of 81 minus 49x squared. Check my Pythagorean theorem if you don't believe me, but it's true. So this sine, oh no, that's not what I wanted. This sine right here, I'm going to throw the negative up high just so I can ignore it for a second. My sine value is the square root of 81 minus 49x squared gross over 9, because it's the opposite over the hypotenuse. Well then, in cleaning this whole thing up, my final answer ends up being dy dx equals, the 9's going to flip up, negative 7 over the square root of 81 minus 49x squared. That is your final answer. Okay, again, because dividing by a fraction is the same thing as multiplying by the reciprocal, so you'd get a 9 over that square root thing, and your 9's would cancel. Okay, not terrible, right? Still just work through the triangle, just get some numbers thrown around, not bad. Let's look at the arctan of x to the 6th over 4. Well, I'm looking to draw a triangle whose angle, y, has a tangent value of x to the 6th over 4. The tangent of y, then, is equal to x to the 6th over 4. I'm going to take the derivative. Secant squared. Sorry, I got a phone call in the middle of recording this riveting video. All right, secant squared of y dy dx is the derivative of tangent of y. So that's why that made that weird jump right there. X to the 6th over 4 is the same thing as 1/4 x to the 6th, which means that when I take the derivative, I get 6/4 x to the 5th. Weird. So I'm going to write that as 3 over 2 x to the 5th. Well then, isolating my dy dx, I'm going to get 3/5 x to the 5th times 1 over secant squared y. And I'm going to choose, for my convenience sake, okay, to do all of this secant squared y over here on the triangle and then fill some stuff in, thinking about it as reciprocals. So this side over here, I'm going to take the square root for my hypotenuse is going to be the square root of 16 plus x to the 12th, because I would do x to the 6th squared. Okay, again, Pythagorean theorem, 4 squared plus x to the 6th squared equals my hypotenuse squared. Solving for that hypotenuse. So if I want the secant squared, I'm going to do some writing. Don't write this down yet. Secant squared would be, secant is going to be the square root of 16 plus x to the 12th over 4, and then I'm going to square it. So when I square it, we end up with 16 plus x to the 12th over 16. No more square. Should have erased that. Now I got to flip it. So it's really going to be 16 over 16 plus x to the 12th. Now, putting this all together, dy dx equals 3 times 16 is 48 x to the 5th over, where did that 5 come from? Whew. Schwartz, keep it together. That should have been a 2. If you're sitting there being like, Ms. Schwartz, that should have been a 2 all along. You are a genius. So this is not 48, this is 24. 24, and then I have this 16 plus x to the 12th, and that would be my final answer. Now, if we're trying to connect this with our formulas that we just came up with, let's look at this chart, okay, where u is a differentiable function of x. The two that we just did, throw in this du dx chain rule situation, okay? What I want to point out to you is that this is when you have u over a. And so instead of 1 minus x squared, when we just had arcsine of x, now we have, this was x over 1, now we have u over a. So u squared and a squared. And if you're looking at this chart and you are feeling overwhelmed, same. What I like to focus on instead is drawing the triangles. And the reason I like that is because it gets at the root of what we study, trigonometry, draw a triangle, or if you're a formula memorizer, here you go.